because hopefully, thank you for letting me know that. Let's see, transcript. That's going to do that at the bottom though, isn't it then? Oh, well, we'll see if that's necessary. We'll try it some other time to remember. Anyways, now you can see that we've got closed captioning going on live. Okay. So today we're talking about chapter 1. Okay. So chapter 1 is the chapter that focuses on, well, an introduction to chemistry. It's like 1.1 is chem as a central science. You got a few definitions there. Matter is a definition. A question I always love to ask on the exam is fire matter? And what that does is it tests, first of all, your understanding of what fire is and your understanding of what matter is. Anyone recall the definition of matter? Or have it in their notes to read? That's perfectly fine too.
Anything that has mass.
Exactly. Now, does fire meet those requirements? No. Fire does not have mass. Fire has 0 mass. Yep. It may occupy space, but it has no mass. And so therefore it does not matter. Okay. What is fire? Can anyone actually tell me what fire is? It's just heat and light. It's energy. It is energy being released. Very, very violently released. That is all fire is. That's why we cannot call fire an element. Okay. Earth, wind, fire, water, heart. I am Captain Planet. No, I'm not. Point being, though, fire is not an element. Fire is just energy being released temporarily. That's all it is. Now, if you got down to the nitty-gritty of it, is there an interconversion between energy and matter? Yes. But that's also different. That is something we have to talk when we talk about physical chemistry and we talk about quantum mechanics, which is something very much outside the scope of this course. Quantum mechanics is a introduction at 3rd or 4th year of university, upper division, multidimensional calculus. Love it. Favorite class I ever took. Anyways, yeah, fire matter? The answer is no. It's a very common misunderstood thing. Fire has no mass, and so therefore it is not matter. Okay. There's a whole bunch of other things in there. You're going to want to know the difference between a physical property and a chemical property, physical change and chemical change. I'm not going to do too much of that. There's already been videos online to support that. The states of matter you're going to want to know, of course, the ones that we talk about are solid, liquid, and gas. There are other states of matter. Those are the 3 ones we typically discuss. There is a 4th, quote unquote, state that we call aqueous. We'll come to that later. But does anyone have an idea what they think aqueous might mean? What does it sound like? With water. Exactly. With water. So it literally means dissolved in water. Exactly. Yeah. See, your understandings of linguistics are like cheat codes to science. Okay. If you understand linguistics, the origin of words, Greek, Latin, and a few other languages, you can understand science and get away with a lot less memorization. Okay. Aqueous is like aqua or agua. Okay. And if you understand how linguistics works, it can be a very powerful tool to make use of in science, not just chemistry, biology and physics as well. So I encourage you to understand the language. The language is so important. And do I love this stuff? You better believe I do. Okay. That's why I'm not boring to listen to. I genuinely love this stuff. Wish I got paid to do it full time. It'd be amazing. The dream. Winning the lottery. Now, classifications of matter, pure substances versus mixtures. Those are things that you guys should be able to go through. Are there any questions about classifications of matter, pure substances versus mixtures, or the types of mixtures? Any questions about that? Any questions? Or does anyone want me to go to a brief description of those things How about we go with, if anyone would like me to cover the material, just briefly raise your hand. Okay. Or, tap your nose if you're not, blink rapidly, unless you have something stuck in your eye. Okay. Moving on from that, I will just mention then outside of that, with regard to substances, just keep in mind, you've got either pure or mixture. Let's get rid of this and actually make it so you guys can see everything. And from pure, you'll either have compounds or elements. Compounds are mixtures of elements, but still pure because they aren't actually what a mixture is. Okay, these are still pure compounds. Elements will be literally the elements of the periodic table, and the periodic table is an amazing device. It's not just useful for putting food on or designing clever memes out of. Anyway, by the way, does anyone know who came up with the term meme? Anyone know the origin of the word meme? Richard Dawkins, famous British biologist. So elements are as pure as you can get. You cannot break things down further and retain recognizable physical or chemical properties once you go and hit element. Compounds will have very reproducible, recognizable properties, but you can still separate the elements chemically and get down to the elemental level. Mixtures will be broken down into heterogeneous and either homogeneous or homogeneous. Both pronunciations are acceptable according to the Oxford English Dictionary. So heterogeneous means, hetero basically means other. So heterogeneous means a non all same mixture. If you were to analyze a heterogeneous mixture, it would be asymmetrical or unblended. The most classic example of this sort of thing is something like a balsamic vinaigrette, which always needs to be mixed back up, or oil and water. That is a heterogeneous mixture, things that separate typically. Or when you throw stew together, the vegetables and the meat don't mix perfectly. No matter how you mix, you go like this, you're going to always end up with a spoonful that has more of one or the other, and someone's going to get cheated out of the delicious whatever they're looking for. Okay. Homogeneous is going to be the same everywhere. Homogeneous means that the mixture has the exact same blend of everything throughout. Perfect example of that is the air you're breathing right now. It is about, let's see, what is it? It is about 70% nitrogen, somewhere between 16 to 20% oxygen. You throw in some CO2, a little bit of argon, a few other things, very little argon. You do not want argon in your air. Argon is heavier than air. It'll literally get stuck in your lungs and you will suffocate if you breathe in pure argon. That's not a good thing last time I checked. Literally, if you find yourself breathing pure argon, they will literally take you and flip you upside down to get it to drain out of your lungs. I kid you not. I know, shocking, right? So the air you're breathing, though, is that percentage, and it is throughout the entire room. Okay, it's not like all the oxygen's over there, because otherwise you guys would be getting up constantly with little straws just to go get your oxygen. And thankfully, that's not a thing. We breathe air very easily. Okay, that's homogeneous. Homo meaning same, the root there. That's the extent of that. That was more than I intended saying. Blah, blah, blah. Chemical symbols and elements. There's lists on their website. I believe I put them on Canvas that you need to know. It's just like learning your alphabet. You got to learn the symbols, okay? You need to know the symbols and know how they correspond to specific elements. It doesn't mean you need to know them for the entire set of elements. You just need to know the ones you're going to use. You're not going to use all of the ones right after AC, for example. You're not going to use, let's see, RF, DB, SG, BH, HS. No one cares about and okay. No one cares. They are artificially made elements that are super, super unstable in a lab and exist for microns or femtoseconds. They exist, they're theoretically there, but they're not things you're going to encounter in nature. Even generally above number 90, which is number 90. Who are you again? Let's see, brain. Yeah, right above, like about your palladium, not palladium. Yeah, I think it's palladium. No, PA is not palladium. It is a different one. But right above uranium, you're not going to generally find most of those elements in very high concentration out in nature. Uranium, yes, you'll find in nature, but in very small quantities comparatively. Yes, we find it. Yes, we build horrible things out of it. But again, an aside. But you do need to learn those, okay? There are a bunch of other things that I'd like to mention from that section, but I'm not going to. Aside from chemical formulas are made from combining elemental symbols and subscripts to represent composition. You need to understand how that works. Chemical reactions. Anyone need any review of chemical reactions, or was that pretty straightforward? Any concern about 1.4 or 1.5? Anyone need a review of 1.4 or 1.5? Okay, moving on then to 1.6, physical quantities, units, and scientific notation. Is anyone at all a little shaky on scientific notation or the concept of units? Okay, would you be willing to tell me which part?
Just scientific notation.
Scientific notation, no problem, absolutely. Okay, so the basic idea of scientific notation is a non-scientific notation number can be anything like 202.3157. It can even be 0.0005376. There's all sorts of ways of writing it because there's only one way of doing scientific notation. And what that is the first position left of the decimal. This will be the first non-zero reading a quantity left to right. I apologize, my handwriting is going to start out a little bit bad because I haven't taught since May. So I get a little bit used to my Wickham tablet. By the second or third lecture, it gets a lot better. That's why I did go to med school. My handwriting is not good enough for scribbling prescriptions. Too many pharmacists would not have been able to read my handwriting. This is too easy to read. The secrets would be out. So it says first non-zero reading quantity left to right. Yeah. And then, so you put that in the position, just one number to the left of the decimal, and then all the rest go to the right of the decimal. And then you multiply it by a factor of 10 raised to the power of however many places you had to move the decimal to get it to that position. Okay, now don't worry. This is basically a storage of information of the original position, that says position, of the decimal. Done correctly, scientific notation just stores information. Okay. Good so far? Anyone need more time? Any questions about what I've written? Anyone need a translator? Like I said, I'm borderline. My older brother is a doctor. Was a doctor? Yes, retired. My younger sister's a vet. I have a very strange family. I'm the black sheep of the family. I don't make money. I'm a very bad Jew. Okay, so if that stores information, what we mean, for example, is if the number is something like 700 7, 1, 2, 3, 4. Apparently there was a 4. There we go. 45.397111. To write that in scientific notation, we need to know where the decimal needs to go. So we're going to move it this way to get it to this position here. That makes sense so far? Has to move that way. So it goes 1, 2, 3, 4, 5 places. Okay. Now, since we moved the decimal left and the value was and is greater than or equal to 1, it'll be a positive exponent. Okay, it'll be a positive exponent. So we had to move it 1, 2, 3, 4, 5 places. So our new value becomes 7.21345,397, because it doesn't actually affect the numerals. 111 times 10 to the 5. Make sense? And if the value is smaller than 1, you just do the opposite process with a negative exponent. That's really all there is to it. I'll show you an example and then we'll move on. Sound good? Okay. I won't even write out all the details. I'll just show you the example. Here is the example of something smaller than 1. 0 point, and you don't have to put a 0 before your decimal, but I encourage you to, because for me, otherwise I lose track of the decimal. If it doesn't have a friend standing guard, I don't know where the decimal is. It's too short. Apologize if I offended any short people. Okay. You get lost in a crowd, right? Hard to reach the tall objects. The decimal just wants to be able to reach things that have been put out of reach. So 0.00005,321. The decimal now needs to be moved 1, 2, 3, 4, 5 places right here. So that means our new value is going to be 5.321 times 10 to the 1, 2, 3, 4, 5 minus 5. Okay. And if you happen to be trying to go from scientific notation to a standard notation, you just reverse the process. Okay. I know I need more time with this slide. Okay. For example, very quickly, I'll just show you a short example. Here we go. So we've got 7.32 times 10 to the minus 11. This suddenly becomes, well, you're going to have to, since it's minus, that means the decimal is headed this way. Okay. And it means that it's going to be 0. This 0 doesn't count as one of those zeros. It's going to be how many additional zeros?
11.
10. And the reason it's 10 is because the first movement is just to the left of the to the left of the non-zero. You were very close, but it's actually n minus 1 because you have to count the first movement to get away from the non-zero. And then it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7, 3, 2. That makes sense? Okay. And if you don't remember that, that's okay. You can also just go write the number way out to the right and just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and fill in the zeros where there is a loop that has nothing there. That's fine too. And if you do that on all the exams and get all the right answers, it might take you a little bit of extra time, but if you get all the right answers, don't be embarrassed because you're actually succeeding in life. If you're the person that decides to do the shortcut and get the wrong answer, you're going to get the lower grade. That doesn't benefit you at all. Okay. Good so far, guys? Okay. Blah, blah, blah. Let's see what time is it. I want to get out of here very quickly. So I'm not trying to run out on you guys. I just want to go home. I'm tired. Been on the go since 6 a.m. love to get home before midnight. Okay, that is scientific notation. How comfortable are you guys with units? The metric system, the international system. Do you guys know the metric system? You guys comfortable with, let's see. So if we have, for example, grams as what we call the base unit, then this is how horrible my, well, horrible slash generous my chain smoking 7th grade math teacher was. She got stuck in my head a little song that helps me with at least 6 of the denominations. You go deci, centi, milli, and then of course after that it is milli, then it's micro, nano, pico, femto, and then to the left you've got deca, hecta, kilo, mega, giga. Now, if we're talking about the base unit, then 1 gram is 10 to the 1 decigrams. 1 gram is 10 to the 2 centigrams. 1 gram is 10 to the 3 milligrams. Does that make sense so far? 1 gram is equal to 10 to the 3. So if we're talking about 1 gram, it is equal to 10 to the 1 decigrams, equal to 10 to the 2 centigrams, equal to 10 to the 3 milligrams. You guys with me so far? If not, please review this video and other videos. Okay. 1 gram is equal to 10 to the 6 micrograms, and that symbol is going to be mu, micro, milligrams, centigrams, decigrams. Now, 1 gram is equal to 10 to the 9 nanograms, 10 to the 12 picograms, and 10 to the 15 femtograms. Now, the only place I've ever seen femto used is when we're talking about seconds. There's not many units that people split down that far. Seconds, yes, but not many others. Does this make sense so far, guys? Okay, now, when you are talking about the larger units, you're going to have 1 gram is equal to, so if we're still talking about 1 gram, the reference point, 1 gram, there are 10 to the minus 1 decagrams. There is 10 to the minus 2 hectograms. There is 10 to the minus 3 kilograms. There is 10 to the minus 6 megagrams, and 10 to the minus 9 gigagrams. It's a capital, that's what it should be. This should be review. This should not be the only thing. This is supplementary material, not meant to be the primary lecture. I hope this helps. Good so far, guys? Okay. Any questions about the metric system? Okay, you'll be using meters for length or some their derivation of. You'll be using, generally you'll be using grams for mass. Know that there is a difference between mass and weight. Weight is gravitational force upon a mass. Weight is gravitational force upon a mass, which is why your weight can be different depending on how much gravitational force is upon you, the moon versus the earth. But you'll always have the same mass. Okay. That's why weight doesn't actually really mean as much as people emphasize. It's actually your mass that matters. Potato, potato, but actually it's all potatoes. No one says I'm going to go get some potatoes. Same with the tomatoes. Temperature, Kelvin, Celsius, etc. Okay, all of this, like I said, review. 1.7 measuring mass and length. That should be straightforward. Anyone need measuring mass and length? Significant figures. Anyone struggling with significant figures? Everyone's got significant figures. You guys all comfortable with significant figures? So come the first exam, when I ask you guys to write things in significant figures, do calculations with significant figures, you're going to be down. Okay, cool. We'll skip that then. I'm fine with that. Sorry?
Can we do
Sure,
it?
no problem. Okay.
Right.
Significant figures are frustrating. I'm not going to give you a huge lot of background on this. Let's just say, oh wow, that was horrible. Apparently I don't like significant figures. We'll call them take two sig figs. Apparently significant fruit. Significant figures do matter because the effort with significant figures is to store information about the actual precision of a measurement. How precise could you measure that? If you measure something at 1.13, whatever units, and you multiply that by another thing that's 1.13, you can only have an answer that has 3 total significant figures in it, because you could not have 1.13 times 1.13 giving you an answer of 1.1 blah, 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 blah. If you put 7 digits to the right of the decimal, you're indicating to a scientist that suddenly you've increased your level of precision, which is a physical impossibility because you can't increase your precision doing a calculation. You haven't done any measuring. It would be completely illogical. Okay. That's why significant figures matter. Now, they're also incredibly frustrating and irritating. I get it, believe me. That's why I'm not going to require you to use significant figures at all times. However, I'm going to encourage you to, because there will be a time if you ever enter the scientific community where you're going to need to be able to do it. And there will be professors that are severe sticklers for it. I am not one of them. I'm just one that is here to make sure that you learn it, and that when you leave my classroom, you can't blame me for not understanding. I'm all about avoiding blame. Okay. Now, significant figures, very simple. You start with the rules of measurement. When you take a measurement, I'm not even gonna write the, okay, so there's a couple of different types of devices. You'll have a digital device, which will have a digital screen and will give you the readout of the measurement. That digital device means you just write down whatever readout it's giving you. Do not write down fewer numbers. Don't write down numbers that aren't on the screen. Do not create numbers. Okay. The precision of the digital device is what it indicates to you. So you just write down the value. And of course, that means we wish all measuring devices were digital, because that would be the easy thing. They're not. Glassware, to my last inspection, is generally not digital. Rulers aren't digital. There's a lot of devices that are not digital. So for sake's arguments, we'll call them analog devices. So digital devices write down the readout, if you will. If your scale says 3.123, write down 3.123. Okay. Analog devices, you write down all the exact precise values, meaning the ones that you can actually see from markings or indications. And I'll show you a very badly drawn idea of that. Plus one estimated decimal or value. Okay. You write down an estimated value. You go, okay, I can read it to this level of precision, and you estimate whatever is in between the marks that you can't read. Okay. And that should make sense to you because you've seen glassware. It'll be 1, 2, 3. And if it's 1, 2, 3, then you estimate it to the first decimal place. You go, it's 1.1. Okay. Drawing of this. If you've got a beautiful piece of glassware like this, see the 3D. I know it's amazing, right? I know. You're very, very jealous of my art talent. You think I work for a VR company. If on the glassware you have markings that you're trying to read that are something like 1, 2, 3, and the actual level of the liquid in there is in between 1 and 2, then you record 1 point, what does it look like? 1 point, a little bit above halfway. So maybe 1.6 or 1.7. You could write down 1.6 or 1.7 and still be right. Okay. I'm going to write down 1.6. This is my estimated final numeral. And that's what the book is talking about. That's what the website's talking about when you talk about an estimated place. That's where you have the cutoff of the last significant figure you write down. And it's almost never going to be 0 because it's very, very seldom that you're looking at a ruler. It's very, very seldom that you're looking at a ruler and it has markings and the whatever you're measuring is exactly right on the mark. It's very seldom. It's always like slightly over or slightly under. And so you estimate that. Okay. Again, if this is something like 1.2, 1.3, 1.4, then for this value right here, 1.5, we'd estimate that at something like 1.41. And this is the value that I then record. Does that make sense? You use the precision that the device gives you plus 1 estimated step. Make sense? Okay, if you forget this, please feel free to ask if you're doing it right when you're recording measurements. I'm happy to answer that. Okay, good so far? Okay, now, when doing calculations, what numbers are still significant? Which ones still matter? And I know I'm writing fast. I apologize. It says, when doing calculations, what numbers are still significant? 1, for a measurement, all non-zeros are significant. Okay. 2, any zeros in the middle of non-zeros. Okay. These are all significant. 3, any zeros to the right of an explicit decimal. Now, at my industry job, if I'd written that, my coworkers would have laughed because they're very juvenile, and you say the word explicit, they think it's a curse word. What it actually means is just a very obvious, clearly indicated decimal. Like very clearly indicated decimal is the one that you can see. The really irritating decimal ones are the ones that are implied decimals. Oh, I implied that decimal by writing a number. No, you didn't. An implied decimal is not a thing. I get so annoyed with the term implied decimal. And it's like, I meant to do something, but I meant to pay you, but you just didn't get paid this month. I meant to come to work, but sorry, I just didn't. There's no excuse. Same thing for an implied decimal. Don't worry about it. If the decimal is there, it's there. If it's not there, it's not there. You don't have to try to figure out whether or not. You don't have to psychoanalyze the decimal. Okay? Not going to happen. No couch, nothing like that. But an explicit decimal is one you can see. All right. So these are the values that are significant. What are insignificant? These are 1, zeros that are what we call leading, And these are the ones that are left of the first non-zero when reading from left to right. Those are leading zeros. Those are always insignificant. They do not matter. They will always be insignificant. Okay. And 2, when no decimal is explicitly there, then trailing zeros are also, this is the really irritating thing, they become questionable. Well, they might matter, they might not. I'm going to tell you that's the rule. If there's no decimal there, trailing zeros are insignificant because you can't know if they are significant. Unless the person taking the measurement is you and you are the one who recorded the value, you can't know. Okay? You can't. Or someone writes next to it, the trailing zeros are significant. There has to be a clear indicator. Okay. The other thing that I will tell you is, yes, there will be quote unquote word problems on an exam. If there is a decimal in the middle of a question, I will put a decimal and then a period. It'll look like 2 dots, but I won't put something that looks like a decimal or a period, because I'm not even going to expect you to recognize whether or not a letter is capitalized as an indicator of a decimal or not a decimal, because that's just a mean game to play on you guys when you're already stressed out. So I will make it clear. Okay? And if you have any doubts about whether or not something's a decimal, just ask. Just ask. Okay? That is a question that even on an exam, I will answer. Is that a decimal? No, it's a speck of dirt. Wipe it off your paper. Good so far? Okay. Now, if we understand what numbers are significant, not significant, I'm not going to show you examples. I'm just going to give you the rules for that. We're way over time. I wanted to be leaving out of here by 7:30. We're way over time. Calculations, real quick. There are 2 general rules. Addition and subtraction. That means adding stuff and minusing stuff. Okay. You have to write numbers out in non-exponential form. What that means is no scientific form, no scientific notation, no notation that utilizes a exponential. And then after adding, keep all significant figures left of the decimal, and only the fewest number of those right of the decimal as number added up. Very simply, example here, 1.1123 plus 2.32. Keep 2 significant figures on the right of the decimal in your answer. Make sense? See, there's only 2 here, so you're only allowed 2. You never have something that is more precise than what you have to work with. Okay. Good so far? Anyone need more time? Question? Stretching?
Yeah.
Gotcha. Okay, that's that one. And then finally, multiplication, division. Multiplication, division is keep the fewest total number of significant figures in one of the numbers used for the calculation. It has nothing to do with left or right of the decimal, just total number of significant figures. So if you do something like 2.3257 times 0.131756 times 9.23157 divided by 0.11, your final answer will only have two significant figures. Because after you do all these calculations, the final one will be based upon the thing with the fewest number of significant figures. Okay. And yes, it gets tricky when you do a string of calculations like that one will require, because you're going to go, well, I had 5. Do I round? Don't round until the end. Just base your answer upon what would give you the fewest number of significant figures. And it gets tricky when you do combine rules of multiplication and division with subtraction and addition. Of course, it's tricky because you have to keep track of how many significant figures. So you go, I've got 7 here. Now I've got 5. I'm down to 3. So at the very end, only round your answer at the very end. Because otherwise you round and round and round and you introduce error. That makes sense, guys? Okay. Any questions? Okay. I honestly think significant figures is probably the most frustrating thing outside of looking at the energetics, the temperature and the energy calculations that are at the very end of this chapter. But that should be something you guys can navigate. If you have questions, let me know. I will let you know later. I'm going to try to post tonight what my office hours later this week will be. Other than that, I'm going to stop this recording here and let's get the heck out of campus.